Welcome to the Crazy Hat Chemist. So today we're doing another video on thermochemistry. Let's get started. Bam! So thermochemistry calculation number 4. I'm going to read the question here again. What is the temperature of water when a 120.0 gram iron weight, specific heat capacity of 0.473 joules per gram degree Celsius, is heated to 125 degrees Celsius and placed in a calorimeter containing 225 grams of water at 25.0 degrees Celsius. So you need to pause the video here at this point in time, and I want you to try to solve the problem, figure out what equation you're using, what numbers you actually have, and plug it in. So look in the bottom of your screen here. This is the equation that we're using. It's very similar to the equation that we used in the previous problem, that is calculation number 3. Except for this time, I've left it as Q metal plus Q water equals 0 instead of doing Q metal is equal to minus Q of water. Doesn't really matter. Both equations are the same thing. So I'm going to substitute in for the metal the Q equals MC TF minus TI, and also for the Q water as Q equals MC TF minus TI. So I'm going to have two equations. They're going to be summed together and they're going to equal 0. So that's what I have right here written out. So the left-hand side of this here is all for the metal. That is the MCTF minus TI for the metal, and plus MCTF minus TI for the water is equal to 0. Okay, now I'm going to find the numbers in which are in this problem here and start plugging them into the places where they belong in this equation. You should see that the mass of the metal is, the iron weight is 120.0 grams. That goes right there. Okay, the mass of the water is the 225 grams. That goes right there. Okay, the specific heat capacity of the iron is given at 0.473 joules per gram degree Celsius. The initial temperature of the metal is 125 degrees Celsius. The tabled value for the specific heat capacity of the water is 4.184 joules per gram degree Celsius. That is the only specific heat that you should actually have memorized, certainly. Okay, and then the initial temperature of the water is 25.0 degrees Celsius. Okay, do we have any other information that's in this problem? We do and we don't. Okay, and that other information is what we are solving for is the final temperature. It says, what is the temperature of the water when? Okay, now that is the final temperature of the water which you're solving for. Ironically, or not ironically really, it's making sense hopefully, because this is reaching thermal equilibrium. And that is the temperature of the water and the temperature of the metal will be the same at thermal equilibrium. So it didn't matter if this question said what is the temperature of the water or what is the temperature of the metal. Okay, both of these are the same number. So now I want you to think for yourself and think about what do you think a reasonable number for the final temperature of the water and the final temperature of the metal would be if I take a piece of metal and dunk it into some water. So the water is initially at 25 degrees Celsius, the metal is initially at 125 degrees Celsius. So once I do all the math on this problem correctly, then should I get a number that is less than 25 degrees Celsius? The answer, yes or no? No. Should I get a number that is greater than 125 degrees Celsius? Yes or no? No. So that means a reasonable number should be between 25, that is greater than 25 degrees Celsius, and in between 25 and 125. So that's greater than 25 degrees Celsius and less than 125 degrees Celsius. That would be a reasonable number. Now, what makes that number really fine-tune in, and if you do enough of these problems, is really truly the specific heat and the mass. The combination of those two things should really tell you what side of this 25 or 125 it's going to be on. Like, which will it be closer to? Will it be closer to the 25 or to the 125? And that is dependent on the mass of both and the specific heat capacity of both, the product therein. Okay, and you should see that the product of the metal's mass and specific heat is less than the product of the water specific heat and mass. So therefore, it should be closer to, think about it, okay? All right. That is the water, okay, because that's a larger number. All right, so now what we're going to do is we're going to plug in those numbers where all those dashed arrows were, and we're going to plug in those numbers. I already mentioned this here, which is the final temperature of the metal and the final temperature of the water are the same, and that's reaching thermal equilibrium. So again, it doesn't matter what this question is asking for, the final temperature of the water or the final temperature of the metal. Okay, I've plugged in these numbers here. I've included the units. Okay, and now what we're going to do is do the math on this. So after this point, there should be a flat-out Algebra 1 problem for you. Okay, so I'm going to take the product of the mass and the specific heat and distribute it over the temperature final and the 125. I'm going to do the same thing here with the water. Take the product of the mass and the specific heat of water and distribute that over the final temperature of the water and the initial temperature for the water. And once I do that, I'm going to start doing the math. Now, when I do the math, I'm going to get rid of all the units. I'm going to put the units back into the problem later on here at the very end. So what am I solving for? A temperature. So my units at the end are going to be degrees Celsius. Hopefully that's a dot. Okay, so now this is what I've done with the multiplication before the distribution. Now I'm going to distribute the 56.76, I'm going to distribute the 941, and then I get these numbers. Okay, I'm going to look at these numbers here now, and I'm going to combine my like terms. So everything with an x is going to be combined with addition, subtraction. Everything with a non-x is going to be combined with addition, subtraction. Make sure you look at the signs. Okay, and then I'm going to move the x's on one side and the non-x's on the other side, so I get rid of that zero term. Okay, that is my next step here. So I'm going to move the non-x's on the right-hand side with addition, and that's moved over there. Then I'm going to divide by the coefficient in front of the x. That's the 998.16. Once I divide by that coefficient in front of the x, and this is the number that I get in my calculator. Now I need to round this to the correct number of significant figures. The fewest number of significant figures that I had in this problem was 3. So I'm going to round this 30.6864 to 3 significant figures, and I'm going to put units associated with that as well. So I have 3, a 0, a 6, and then that last digit there is that 8. I'm using that 8 as rounding. That 8 is 5 or greater, so I'm going to add 1 to the preceding digit. That 6 becomes a 7. I'm going to slap some units on there. And that's why I get this 30.7 degrees Celsius for my final answer, 3 significant figures with units on it. This is the final temperature of the metal, and it's the final temperature of the water as an answer. Either of those would work. Now, going back to, is this a reasonable answer? Does this answer make sense? It most certainly does, because this answer is in between the initial temperature of the metal and the water. And it is closer to that of the water, because the product of the water's mass and specific heat is greater than the product of the iron's mass and specific heat. Okay? Make sure you review that one. Okay, the next video is coming up pretty soon, but here's a crazy hat for you. And this is a basketball, so if you like shoot and hoop, then this is a super one. Okay, and if you do like shoot and hoop, then this is actually kind of fun, especially with this basketball. Give me a thumbs up if you like that video. Subscribe to my YouTube channel, and wait, I'm going to shoot hoop. It's going in the hoop. Whew.